So, as was introduced, my name is Eric Reese. I was introduced as somebody from a company that begins with K, but I'm actually here representing the Software-Enabled Flash project. That's not working, so I'll do it that way. The Software-Enabled Flash project was actually founded this year, something that we've talked about and worked towards for a long time. And as of this April, it's official. It's an official project being hosted by the Linux Foundation. A little bit of nostalgia. This is my fourth time to present to this conference. The second time to do it live and in person. And it's really, really nice to be able to be back and see all your shining faces. And it's really nice to not be looking at a camera while I'm doing this. Over the past, actually going to 2017, we've been working on this concept of software-enabled Flash. And in previous presentations that I've made to this group, I've talked about some of the unique features of Flash, how it's fundamentally digital, how it's something that does not need to be treated as a drive. And that was some of the steps and thought processes we had in bringing forth the idea of enabling Flash for software. In the course of those presentations, I also talked about our intent to be able to make software-enabled Flash an open source project open to all of you. So Flash as a storage medium is something that's unique. It's digital, and I don't need to explain to you how much software-defined has changed storage over the years. But there's been a level to that where it stopped at the device level, and it doesn't need to do that anymore. It needs to come down all the way to the device, and that's what we're bringing. And right here, proof is in the pudding. That's what we're doing. Also, Flash happens to be the costliest commodity in the data center. But ironically, in many ways, it's underutilized still. So with software-enabled Flash, we want to bring to you the ability to integrate that Flash into the software stack, to be able to bring it under your control as developers, and thereby ease the deployment and make the deployment of your storage more efficient. One of the goals that we have with the software-enabled Flash project is to be able to spread the goodness of Flash throughout the data center much more ubiquitously. Right now, out of necessity, there's a mix of different kinds of storage. I'm not saying that shouldn't happen, and I'm not saying that should go away. But I am saying that there's a strong value proposition for using and deploying Flash more broadly within the data center. And therefore, we want to make that much more easy for you to do. So we have brought this to open source. It's open to everyone. It's neutral to everyone. And it's also, because it is open source, available to stakeholder input. Now, in terms of that openness and neutrality, it's vital that we do that so that we can raise all the boats within the industry, and also to avoid having one voice dominate the specification or the overall definition of this technology. So it's open to all vendors. It's open to controller manufacturers. It's open to developers. We've already been able to hold a couple of technical steering committees. We'll be holding another technical steering committee in the near future, and we certainly welcome your participation. I made mention of stakeholders. In the development of the concept of software-enabled Flash, and then in the development of the technology itself, we spent a long time engaging with stakeholders, various stakeholders. Those who are potential users, those who would be potential suppliers of different technology controllers, also with developers such as yourself. And through all of those conversations, it's clear that there are basic functions that need to be brought under the more direct control of the host. You can see some of those functions listed here. The important thing that we've learned, though, is not so much that the host be able to control these things, but that these functions become adaptable to the workloads so that the workloads don't have to adapt to the functions. Within this, you'll see latency there. Latency is one that is usually one of the hotter topics of host management. And there's many arguments. Should your latency be fast? Should it be tilted towards performance? Can it be scattered? What about those nasty latency outliers? All of these things. What is clear, though, is that latency is a subjective term and subjective to the workload. So through software-enabled flash, we want to allow you to be able to control your latency rather than having latency control you. As I mentioned earlier, we've intended to bring software-enabled flash to the open source from the beginning. And as those who've invested in the development of this technology, there have been a lot of questions, why would you want to do that? We want to do that because, primarily, nothing can succeed on its own in the market. You need to have multiple sources. But on top of that, we also have a vested interest in seeing flash become more broadly used. As flash becomes more complex in its programming methodologies as well, there's a need there's a need to be able to make it much easier for you developers to use it if we want to have it become used more broadly. Therefore, there's a lot of potential we want to unlock to you. I mentioned the functions previously. There are other things that affect its value proposition. There's the costliness of it. One of those things is over-provisioning. Some of those things happen to be the housekeeping functions that have to be done to be able to make flash usable. All of those things now are going to be under the control, under the management of the application, helping you as developers to be able to squeeze as much of that value out of the flash as possible, hopefully making you look like superheroes to the business leaders so that they say, hey, more flash, more flash. I'm going to do a little tap dance right there. So a little bit more about the goodness of software-enabled flash. In this conference and throughout the industry, you'll hear the references to different protocols out there that are offering various forms of host control. And I'm not here to say one is better than the other or to say anything bad about them. I think they all have their purpose. But the key about software-enabled flash is that it's software definable. Therefore, it supports all of these, and it can support all of these different protocols. In fact, one of our first proof of concepts that we did many years ago on a single drive had all of these protocols running simultaneously under different workloads. So from the beginning, it's been our intention to support what's out there. So if you have a need to be able to have a software-enabled flash drive function as in any of these protocols, you can do it. You can do it simultaneously. I don't know why you'd want to, but if you need to do it on the fly, you can do it on the fly. But again, we support them. It's software definable, and I'm not going to say what is better than the other. The different protocols can fight it out amongst themselves. We'll just let you support them all. And Earl over here will tell you how it's done. Now, an interesting trend in data centers over the past has been this penchant for some of them to want to make their own SSDs. As flash is becoming more and more complex in how you program it, I'm seeing that the tendency or desire to do it on their own, to make their own SSD, seems to be coming off a little bit, although some are still hanging in there. And there's a simple reason why it was a trend, and that there's those who are still hanging in there. And that is that there is a need for a level of control, a need for a level of management that just isn't available with the standard SSD. And so that is the problem that software-enabled flash attempts, and we think now successfully resolves. Now, how is that done? It's the Ceph API. Ceph meaning software-enabled flash, it's the API. If you program to that API, an SCF drive will function out in that way, and also the drive in the background will manage the media according to the best way that the media needs to be managed. As you program to that API, in the background, the project will determine with its members what changes need to be done in the firmware or in the hardware with each new geometry so that it just works to the API. And thus allowing you to focus on what's most important to you in your development efforts. So I kind of pitched ahead of this slide, but in this slide I was going to talk a little bit more about that API. It's vendor neutral. It's designed so that if you develop to it, going forward, your storage will just work. Flash will continue to migrate from generation to generation, from complexity to complexity, and hopefully maybe not so complex. Vendors will do what vendors do. But if you are adapted to that technology, if you're adopting this technology, you just need to worry about the API. And your storage will work in the software-defined manner. The functions that I talked about earlier, you can manage them as you need, without having to redevelop and redevelop with each new announcement of technology. The benefit to the data center is that they can stay on the cutting edge of the evolvement of flash without having to wait for months and months or maybe even years to be able to get to that new geometry. Because with the software-enabled flash drive, those things are abstracted out. So for you as a developer in using SCF, you should be able to develop faster. You should be able to have more adept control over your storage. And I'm saying should, but the actual fact is when you do it, we've tested this, it does work. Managing your storage performance deterministically according to how you need to run your workloads is something that's available to you. Therefore, easing the deployment of the storage that you are programming to. Finally, you have a voice in how things are done because it is open source. Please come to the technical steering committees. Please participate. I encourage you and your employers to join the project and make this something more exciting. So to summarize this point, this part of the what is SCF, what is the software-enabled flash project, let me just summarize a few things. It's open to everybody. It's neutral. Other vendors, other controller suppliers, Marvell is already involved, are involved or are looking to be involved and will be involved in the future. Therefore, it will be something that's multi-sourced. It will be the best way to deploy your storage going forward in a software-defined world. It'll be the best way for you to be able to manage your performance because you will determine what your performance is and you can design your application and the storage to perform in the way that best suits you. So, to summarize, we are enabling you to control the functions of your drive and not have the drives define the function of your software. That concludes my portion of the what. I want to be able to turn it over to my colleague in the project, Earl Philhauer. He's not Scott Stetzer. Scott Stetzer's having a technical difficulty, although he is here. Earl will then talk a little bit about how this is all done.
Yep, thank you. Thank you, Eric. So yes, I apologize. I'm not Scott Stetzer. He did have a quote for you guys, a little prepared speech. Let me make sure I get it right. He'd like me to tell you that you came here for Scott, but there will be no refunds. So that said, I thought it was funny. Let's carry on. Eric gave a really good discussion about kind of the why software-enabled flash is important, why you're going to be seeing it out there in your deployments, why you're going to want to use it. I want to go a little bit into kind of double-clicking into it, go down into the details so you can get just kind of an overview of how it happens, what's going on behind the scenes to enable this kind of power. So the key is this is custom designed hardware and custom designed software built to give you, the developers, power over Flash without needing to actually become a Flash guru. It's based off of a custom engineered hardware platform that is built to abstract the low-level details of Flash out of the picture, so you don't have to worry about it. Again, we talked about being multi-vendor, right? We don't want this just to be from one point solution. We want it to be available throughout different vendors in the industry. And to do that, we've actually abstracted it and given choice to the people that are building the hardware, whether they want to use a QLC or TLC or PLC or some other kind of magic flash. Whether they're going to speak on fee or toggle, which are low-level flash protocols, or, for example, how they're going to do the DRAM on the system, whether they're going to use host DRAM resources for everything or they're going to include it in the drive. All of that is configurable by the vendor and supported under this one software-enabled flash API. That's really the whole idea, to give this choice to people to expand the ecosystem and grow better. In fact, the first drives, the ones that are actually out on our table out front, they're built with third-party silicon from Marvell as the controller. So we're starting out on the right foot with this kind of idea of being multi-vendor, very open about it. The hardware, we didn't just decide to throw out new hardware just for the heck of it. We kind of thought about, how can we enable this latency control? I think Eric said, you control the latency doesn't control you now. Well, how do you make that happen? You really have to have a complete redesign of the data path on the drive. We've started by doing a massive number of parallel queues. One I/O queue per flash die. In fact, there's two I/O queues, one for reads, one for writes, to avoid head-of-line blocking. We couple that with three different modes of I/O prioritization. And these come as default options, and you can set at a workload level, default whether you're going to have a priority queuing where one workload always wins over another, a nice fair round robin, or whether you're going to do something called die time weighted fair queuing, which is a really advanced way of saying I want to get exactly this sort of read-write ratio on the flash. What that enables is it gives you the power to define the defaults for the workloads, but beyond that, it's even more powerful than that because it's not just defaults. Individual IOs, if you have an IO that's important, you can actually specify and change the queues and the queuing modes for that particular IQ to say, bump it up in priority or knock it down. If you're doing just a background scan, keep it nice and low, don't interrupt the foreground work. Or if this is, a user query or like an ad server or something, you need to go in a millisecond basis, bump that IO up. All under application control on this standard software-enabled flash drive. The other thing we discussed, and actually Mr. Gritter talked about it earlier, is communication. Moving data back and forth is actually pretty onerous. It's onerous in HPC, but it's really bad even in a regular system with software, with SSDs today. For example, if you're doing something like a database compaction where you're kind of getting rid of the stale pages in your tables, or like a log structured merge tree, say RocksDB or myRocksDB, where you're combining different streams, reading out newer streams and writing out a longer lived stream. That's really just data movement. You're moving data from the drive into the host, doing no real work on it, and then driving it back to the drive. That's wasteful. That wastes your CPU, that wastes your PCIe bandwidth, and with PCIe 5 and 6 and the drives we're pumping out, that's actually a pretty precious resource. What we've done is we've enabled a copy offload function right in the drive in the hardware. This is built to allow these sorts of common operations to be done without host CPU intervention and without DRAM requirements on the host. A simple workload can send down a single command that will collect effectively a series of, we call them ADUs, think of them as LDAs or sectors, and rewrite it in a new spot, all behind the scenes. A single command does all that work. You can use it for things like, I talked about DB compaction, LSMs. You can also use it for garbage collection too, which is the standard flash operating mode for a standard drive. So you've heard about that. It's a really powerful abstraction level that it just makes a lot of sense. With that, to get latency, right, we've got the queuing modes, but the queuing can't help you if you can't keep workloads separated. If you've got one workload that comes up and becomes very chatty, and it's going to the same spot as some other workload, it doesn't matter what your queues are, that other workload's gonna get impacted negatively. So we thought about that, and we came up with two different models, or actually two different ways of isolating workloads from each other to help guarantee that latency and make you guys the masters of the latency, not the drive. The first is called a virtual device, which is a hardware level isolation of workloads and data on a per flash die basis. So this is really cool. As you deploy the flash, a standard drive, you can pick out and choose and say, this area of flash, these number of dies go for one set of workloads, these go for some other set, and never the twain shall meet. I mean, this is perfect isolation. An erase on one virtual device can't impact the performance on another because they're talking to two separate spots. Again, it's user configurable, it's software defined. You pick out what makes sense for your particular deployment. With the hardware isolation, it's on a flash die basis, which today can actually be really, really coarse-grained because our flash die are really, really big. And they're getting bigger and bigger and bigger every time we add more layers or we go to add another bit to the cell. So to kind of offset that, we have a software layer of isolation called the quality of service domain. The quality of service domain is very fine-grained. Think of it as a per workload based isolation, and this is really dynamic. They can come and go, matter of milliseconds. The idea is to isolate workload data sets on a flash superblock basis. A flash superblock is kind of the agglomeration of flash units that are written at a single time. By separating this data out by workload, we're able to isolate one application's chattiness from another. Garbage collection, for example, is caused when you've got kind of stale data in one of these superblocks. Well, if the workloads are isolated and one workload can't write data into another one superblock, that other application can't cause a garbage collection need, for example. That's one really cool feature of this. Another really cool feature is, I know people are looking and saying, I need a read optimized drive or write optimized drive today. And the way that's done a lot of times is through the active over provisioning. Basically, you set aside a larger portion of flash on a write optimized drive than a read. But it's a standard SKU. You buy a different drive to do that. Here, with this software defined way, a single drive, a single quality of service domain can have a different over provisioning level on the same drive than another one. That's a really neat thing. So you can have both read optimized and write optimized workloads simultaneously on the same hardware, and it just works. It's really neat. But that's all hardware, right? I mean, I'm an EE, so the hardware side's the stuff that really, it gets into my blood. But I know this is a software conference, and lots of software developers. You're writing storage array code. You're writing, distributed applications. The software stack for software-enabled flash, well, it's right in the name, it's important. It's built, as Eric said, it's all open source. The idea that we want you as developers to get the code, to use the code and kind of share your upgrades. Everything running on the host is open source. It's a BSD 3-clause license. So it's very permissive as far as open source licenses go. And the idea there is this code, the software stack, it's not a monolithic chunk of data. It's not a million lines in one function. It's built in different modules. It's built for you as a developer to come in and customize individual modules, throw them away, add stuff of your own IP for your own products. And I'll talk to that a little bit in the next couple of slides. There's two different levels really of abstraction, or two different components to the software stack for software-enabled flash. Pre-existing today, and it's been out for about a year if you go to our GitHub, is the software API. So this is a very thin wrapper over the hardware. Things like that write command that did the copy offload, there's a single function call that does it. It's very low level, but it lets you, as a developer, if you really want to access the flash at the lowest bits, but not worry about things like programming time and erase time and, oh, what vendor am I talking to? You can write to that level. That exists today, that's out there. Coming later this year, there's going to be a software development kit, probably like November-ish. Our engineers actually are furiously typing away right now, fixing it, or developing it and, fixing the bugs. You know the drill. It's coming later, and it's going to contain a much higher level of abstraction. It's going to include a user-level FTL, which is a flash translation layer. Basically, this is the stuff that makes the flash chips look like a drive to an application. It's going to include virtual device drivers, so VirtIO drivers that make software-enabled flash drives look like traditional types of drives to virtualize guests. FIO or FIO, the testing tool, very low level testing, very low effort testing. We've actually ported an engine for software-enabled flash, and we've obviously got a CLI that does things like lifecycle management, deploying, et cetera, et cetera. Now, the FTL, I think, is really kind of the coolest thing. Again, source code is provided. That's the whole idea. That's why we're open source from the Linux Foundation. And it's built really to run in individual applications. So you will have the capability of customizing an FTL per workload. So if you've got, say, a storage type workload and you're doing a blob store, you can have a different FTL running than, say, a database FTL at the same time on the same hardware. And you can change things, move them around in real time to different servers, and it'll still just work. The FTL is, again, it's modular. It's modularized. It's not a million lines of code. It's a easily digestible chunks. The idea here is, like Eric said, some people are already building their own flash translation layers or drives. We want you as a developer to be able to take your existing code, all your knowledge, and plug it into the right spot, and let us worry about, the rest of the types of management. The FTL also, because this is running on software-enabled flash, it supports the isolation, it does the queuing modes, et cetera, the latency control, all the good stuff of software-enabled flash, and that's kind of a given with this. Now, we will be providing the source code, but we also, we believe in documentation too. We're big on Doxygen in terms of actual code discussion, but we also do theory of operations and things like that will be made available at the release time. Again, this is open source. You get to go in, dig in, find the stuff that works for you, find the stuff that doesn't, pop in your own code. I spoke about the QEMU, the VirtIO drivers, which are neat just in an abstract level, but they're also really powerful because what this means is you can run workloads today on a software-enabled flash drive with no changes because the QEMU, the virtualization layer, the hypervisor, will actually implement the software-enabled flash primitives to make it work on the drive. What that means is you can get all the benefits of this isolation, this latency control, for a workload without changing those workloads at the higher level. It's a really fast way of testing how it works for you, prototyping, maybe even deploying real applications in the real world. We have today running in our labs emulations for a standard block drive. So it's just a series of LBAs. Everybody knows what that is. A zone namespace drive. It's a series of zones, as well as an NVMe emulation. Again, it's all with the power of the queuing modes, isolation, et cetera. It's all built in, and all the source is there. It doesn't work for you, or you need a different sort of FTL. You've got the source to start with to plug in your own magic. Speaking of magic, Eric did discuss, we've got engineering samples in our labs right now, and the engineering team are furiously working on bring up, et cetera. But they do have some demonstrations running today that are really neat. The one I'm going to show right now involves the workload isolation. We talked a lot about physically isolating workloads, and because of that, the workloads can actually interfere, can actually cause hiccups in performance one to another. Well, let's actually see that in practice on a real drive in this recording. So we've got 3 workloads that are going to start up: a read, a write, and a mixed workload. And you'll see as we pull away, as we turn off individual workloads, the performance of the other workloads is unmodified. It just works. And it stays constant as we pull things off. We're going to re-add those workloads, and you're going to find, again, the performance doesn't change on the remaining workloads. That's the whole idea of the isolation. It's a simple demonstration, but it's really powerful. It kind of puts into visualization what I'm talking about keeping your latency under control by isolating things. This also, if you look at the graph closely, you'll notice that it's an array of 32 individual, these are actually flash die. And you'll see there's some unused flash die. And again, this is a demonstration of the ability that software-enabled flash has to separate workloads, to the die level. In a real application, it'd be really wasteful to have all that unused flash dies. We're just doing it for visualization right now, but you got that power. That's a really, really neat thing, and I'm really proud of our engineers getting this going. In summary, Eric said it really well. It's all about getting Flash, making Flash more valuable to you as a storage array vendor, as a database author, as a storage administrator, as a cloud provider. We're trying to focus on giving you power over Flash at the application level without needing to become Flash gurus, without needing low-level expertise. The fact that we give you this isolation hardware, software, the queuing controls, the massively parallel queues, the copy offloads, coupled with all that software, all the open source software, the SDK, the API, the FTL, the CLI. There's a lot of acronyms. I can go on. It's all about better application results, better use of the Flash that you're deploying, because Flash is important, Flash is powerful, Flash is changing the world. Let's make it easier for you to use it and get the most out of it. So how can you get some more information? How can you actually get involved here? It's pretty simple. So we have a table right outside. We've got our engineers, and they love to talk. They're really friendly. They don't bite. Stop by, give them a chat. We also have a Birds of a Feather that will be Wednesday at 7 p.m. We're trying to get catering right now to get you some food as well. But I can guarantee there's going to at least be food for thought when we talk to the people. We're going to have Rory Bolt, who is he's a senior fellow here, but he's also the TSC chair, Technical Steering Committee chair for the project, as well as some of the engineers and folks that have used this product, or this technology. Also, I see everyone here, well, basically everyone's either got their phone out and they're tapping, or their laptops. go to softwareenabledflash.org. There's a QR code out on our table if you don't want to type it out. Just type it in right now while you're doing it. Put it in a tab. You can look at it later. It's an open source project. It's run by the Linux Foundation. Our website's got some really cool documentation. It's got a lot more videos with a lot more in-depth description. It has links to our GitHub where the source code is provided. So you can actually take that down and take a look at it and start tearing it apart and figuring out how you can use it. And again, you can actually join the project. You can join individual contributors. You can talk to your companies, see if they're interested in. But you don't need to be a member to be part of the project. You can attend our TSC meetings. You can join the mailing list, which is also available on that website. It's very low effort, but it's a very easy way to get involved. So softwareenabledflash.org. Take a gander. And this is all about you, right? So to make this happen, we've spent over 4 years, like Eric showed on his nice little chart, with our heads down, talking to you guys, talking to ourselves, and late nights coding and designing stuff. But to make it useful, to actually rubber meet the road solutions, we need you guys. So with that, I'd like to thank you all for your attention. And again, softwareenabledflash.org or our table right outside. Thank you.